All right, this unit is called the Fundamental Theorem of Calculus. And before we talk about undoing derivatives, we're going to spend a minute and we're going to review the derivatives for these functions. So I want you to take a minute and I want you to try to take all the derivatives for all 6 of these. All right, so here are our derivatives. Hopefully you didn't have to look up too many of them. I am guessing one of them that you had to look up was this inverse tangent. We'll do some more work with that one. And I bet you probably had to look up how to take the derivative of 3 to the x. So hopefully it wasn't too much to look up, but I know those are some places that kids normally struggle. So when we start working with integrals, that will definitely come into play. All right, review question 2 is about the connection between position, velocity, and acceleration. And so what we learned in first semester is that as I go from position to velocity to acceleration, I am taking the derivative. What we're going to learn this semester is how to start at acceleration and how to go up. So how to go up the function. We do that with taking the integral of those functions. And so we're going to just review the connection. So take a minute and try to answer these questions. And then we'll compare our notes. All right, so I've got the answers for the first 3. Question A, it says find the change in position. So that's literally, we're just saying the place at 2 minus the place at 0 to change in position using that position function they gave us. Finding the equation for velocity, that is the derivative of position. So S prime is the same thing right there. Then finding the acceleration function, that's the derivative of velocity. So we would start with the second derivative of position and the derivative of velocity here. That's our acceleration function. So we're just taking the derivatives. All right, so the next 3 is really starting with this unit and what we learned from the intro part of this unit on taking the integral. So look at the average value and we're going to integrate these functions and see what we notice. Okay, it is perfectly acceptable if you got stuck somewhere in this because again, this is where we start building in some of our new stuff. So question D says find the average rate of change of the position function or average velocity. So that's where we take our change in position divided by that space. So change in y or change in x. We're going to take what we did in A, that answer 16, and we're going to divide it by 2. We get 8. Question E says integrate the velocity function over the interval. So what do you notice? So if I am here at velocity and to move up, to undo that derivative, I'm going to integrate. So what we're writing is the integral of 0 to 2 of this function. If you put that in the calculator, that's going to give you 16. And so let's talk about why it gave me the same thing as A. So if I think about starting in velocity when I integrate, what function does that take me to? That literally takes me by definition to the position function. So the integral of velocity, v of t dt, by definition is our position function. So it makes sense then that when I integrate velocity, I should end up with the same thing. We had s of 2 minus s of 0 is 16. We get the same thing as A, and that should happen. Now let's look at F. So we're going to use the calculator to then find the average value. So we found the average value. We had that value already from question E. So now we're going to have 16 over 2, which gives me 8. And so what is that? That's the same thing as D. And so let's talk about why that's happening. So when I take that average value, that is the same thing as that slope between 2 points. So that's where when we integrate, so I'm going to integrate that just like I did in the previous problem. I'm going to have s of 2 minus s of 0, but now I have that space of 2. So these are all connected to each other, and we're going to explore that some more in this unit. Okay, so example 1, now we're getting to the good stuff. So we have this graph of the velocity function, and so the question is, given the following, write an expression that will give you the change in position or the displacement. So one of the things we're really going to talk about a lot is how position, velocity, and acceleration are related. Again, as I stated earlier, when you go from position to velocity and velocity to acceleration, you are taking the derivative. And what we're going to learn to do this time is, as I go from acceleration to velocity, that means I'm going to integrate the function. And as I go from velocity to position, again, I'm going to integrate the function. So this is just kind of a definitional thing. So integrals are going to undo the derivative. So when I write this, I'm going to take the integral of that velocity function. And it looks like my graph is labeled 0 to 10. And what that's going to do is that's going to give me the change in position. It's not going to give me the final position because I don't know where it started, but it is going to give me the overall change in position. And so you might be thinking to yourself, well, how are we going to do this numerically? And so that's kind of what we're getting to in the next few examples. So example 2, we have a car's positions given by this function. What's the car's position at 0 seconds? So we're plugging in 0. We're plugging in 10. So take a minute, plug those into your calculator. Okay, so hopefully you put them in your calculator, and we got at 0, I'm starting at 25. We should be able to look at this equation and just see when I plug in 0 for t, I get 25. Plugging in 10 hopefully wasn't too awful. So we're plugging 10, we get the 25 and the 475. Question C says, what's the change in position? So change in position, you're literally just subtracting them. That's not new material. That's nothing new that we're learning. So this function, this car, has changed by 450 units in position. How does this relate to the previous example? Well, if I had the velocity, so the integral of 0 to 10 of velocity, that is equal to that change in position. Make those nice parentheses. So these are equivalent statements. This is all about just going back and forth in the notation. This is known as the fundamental theorem of calculus. You will see this abbreviated as FTOC for fundamental theorem of calculus. And so all that means is that these derivatives and integrals undo each other. They made a very complicated way of stating it, but it just means derivatives and integrals undo each other. All right, so here we are, example 3. This is the first time we're looking at how do we do this algebraically. So let's think about this concept of the fact that derivatives and integrals undo each other. And I need to think to myself, this function 3, that is the derivative right there of what function? So I need to think to myself, 3 is the derivative of what? When I take a derivative and I end up with 3, what was that function that I took the derivative of? Well, that function happened to be 3x. And I need to know evaluated. So the function is 3x evaluated from 2 to 5. And so what we end up doing algebraically is I say to myself 3 times 5 minus 3 times 2. And so I get 15 minus 6, and I get 9. Now, let's connect this to what we learned about this notation in our previous unit. So our previous unit, that introduction unit that we had this function y equals 3 right here. And we were looking at the area of the rectangle from 2 to 5. And so we were looking at this area. And so right there, it's pretty clear that this is a 3 by 3 square. That area is 9. What we want to do, though, now is we want to not have to draw this every time. All right, so I'm going to look at B. B has the integral of just dx. So we're going to think about dx. I want to really think about like that's 1 dx. So I'm going to say to myself, 1 is the derivative of what function? So like, remember, derivatives is slope. So like 1 is the slope of what function? Well, that function is literally just x, and it's evaluated from 3 to 6. So what I'm going to do is I'm going to say this turns into literally 6 minus 3. We're plugging it in the same way we did the previous one. 6 minus 3 is just 3. So we can draw that picture geometrically again. It's a 1 by 3 rectangle, but the idea here is to bridge this gap so we don't have to do that. All right, so let's look at C. I need to say to myself, x squared right here is the derivative of what? So we're going to go up a power, x to the third. But there has to be a number here because when I take the derivative of x to the third, I end up with a 3x. But that 3x was canceled. So I need to think about what number was there that cancels with a 3. So if it was x to the third, there has to be a 1/3 in front of it. Because now when I take that derivative, this 3 is going to come down. It's going to be 3 over 3, and it cancels. So it's going to be 1/3 x to the third evaluated from 0 to 3. Now, I love doing these simple ones where it's 0 because when you plug in 0 to x to the third, it's just 0. So when we practice this a little bit, we can get kind of lazy with not having to worry about plugging in the 0. So I'm looking at 1/3 of 3 to the third minus 0 to the third. And I'm kind of lazy, so I don't write that 1/3 any more than I have to. So 3 to the third is 27. A third of that is back to 9. So the answer is 9. All right, let's look at the next one. The negative 2/3 power. So let's think about what's happening here. We're going up a power. So it's the opposite of taking a derivative. So a derivative was subtracting a power. So we're thinking to ourselves, x to the what power? When I subtract 1 gives me negative 2/3. So if it was a 1/3 power, we can test this. 1/3 minus 1 does give me negative 2/3. Okay, so I'm good to go there. And I need to say to myself, remember this 1/3 comes down when you take that derivative. So there was a number in front there. The number in front there had to be a 3. Because when you take the derivative here, we always kind of check it when we're starting. This 1/3 comes down and cancels with that 3. That's why there's no number there. So this is our function that we're taking the integral. So, okay, and it is evaluated from a -1 to 8. So we're going to say 3 times, essentially this is the cube root. So the cube root of 8 minus the cube root of -1. I don't know about you, but my brain just processes it better when I actually write it as the radical as opposed to the power. So the cube root of 8 is 2. So I have 3 times 2 minus a -1, so plus 1. I end up with 9 is my answer again. Interesting how several of these keep being 9. I swear that's not a thing. That's completely by accident. All right, so let's look at E. So 5x to the third, that is the derivative of something. So the first thing we do is we go up a power. So it's going to be 5x to the fourth. But keep in mind, this 4 is going to come down and multiply, and it's actually 20 when I take that derivative. But I don't want 20, I just want 5. So what I need to do, there's kind of a trick. You actually go up a power and divide it off. So it's over 4. So that way when you take the derivative, that 4 is in the denominator and it's going to cancel. So now this is evaluated at 0 to 2. And so again, this is another one of those where that 0 is going to be nice. You can just ignore it. So we're going to plug this in, 5/4, that's a constant. So I'm really not worried about him. I'm really worried about what 2 to the fourth minus 0 to the fourth is. So 2 to the fourth power is 16. So I end up with, and I'm going to write this kind of 16 times 5 over 4. And I do that because that 16/4 is what's going to cancel. 16/4 cancels to be 4, so this is going to give me 20. You will experience these problems that are on the no calculator portion of the AP test, so it's important to think about some of these algebraic strategies. You don't want to waste time multiplying 16 times 5 only to turn around and divide by 4. That's a waste of time. All right, let's look at F. Temporarily, I'm going to think about F written as x to the negative 1/2 power, just so that it's easier to integrate. So I'm going to go up a power. So I'm going to say x to the 1/2 power. And essentially, I'm dividing 1/2 off. So dividing by 1/2 is the same as multiplying by 2. We can check this real quick to make sure that this works. The 1/2 is going to come down and cancel that 2. You're going to subtract 1. And we're going to get back to our negative 1/2. So this works. This is our integral. And it's going to be evaluated from 4 to 9. So we're going to plug it in. So I have 2. And again, I'm going to switch back to the square root. So the square root of 9 minus the square root of 4. The square root of 9 is 3. So I have 2 times 3 minus 2, which is 1. So I literally end up just with 2. We'll do some more practice with this in class. We'll do a few more examples, and after some time, you'll get more comfortable with it.